This is one of the harder string search problems, and here we are given a list of words beforehand, and that list will not change. But once we have stored that list of words, and we will see how to store that. Once we have stored that list is fixed, then we will have a bunch of queries coming to us. And in each query, we will have one letter, let's say C. In the next query, we will have another letter, let's say D, and so on. So what this query will return, it should return true or false depending on whether this character is one of the words or not, or this character, and you can include any of the previous queries which we have made. So for example, the first query we have just C, there is nothing before that. So if C is not in the word list that we have just inserted, we will return false. Next query is D. If D is there in the word list, then we return true. But let's say D is not there, but CD is there. So we will return true. Next, let's say E comes, then we will check for if E is a word, or DE is a word, or CDE is a word. So you are allowed to include any of the previous characters, previous queries. You cannot skip any of these. So these should be contiguous. So either just E is present, or if not E, then look for DE. If DE is also not present, look for CDE, and so on until you reach the beginning. So you are allowed to include as many characters as you want. So let's look at an example, then it will be much more clear. And it has been asked in Google and Facebook interviews, and it's one of the harder problems. So here we are creating a storage for these words. So the dictionary will have just 3 words in this example: C, D, F, and K, L. And next, it queries for A. So there is no query before it. So only possibility is to search for A. So A is not present. So it returns false. Then we have B. B is also not present. So we will search for, here we search for A, here we search for B or AB. So you are allowed to include previous ones. So both are not present. So it returns false. Then we have C. So we search for C, not present. BC, not present. ABC, not present. And now there is no place to go. So we return false. Next, D. So D is not present. So we look for CD, but CD is present. So CD is found, and it returns true. Next, E. E is not there. DE is not there. CD is not there. Similarly, none of its prefixes, including this, are there. So it's false. Now F. F is itself there, so no need to check further. As soon as we get end of a word in the storage, we return true. Then G is not there, neither FG, none of these are there. Similarly, you cannot find H, GH, FGH, EFGH, any of these. I is also not there, any word found by one of its prefixes is also not there. Next, L. L is not there, but KL is there. So we return true, no need to check further. So how can we do that? So one straightaway thought would be there that we should store this in a trie or a prefix tree. But here you see that if we store CD, so C, D, then F and K, L in a trie, then we are not searching like this, LK, it's KL, so it's fixed. So here, for example, in this case, we searched for L, then we search for KL, or let's take a negative example. Let's take this example. So we searched for H, then we searched for GH. So while searching for GH, we have already searched H, but again we are starting from G, and again we will match H. Then we will search FGH, and then we will search EFGH. And in the worst case, if we have, let's say, 100 queries already made, then we will search 100 times in this trie, and each word will be 1 length, 2 length. So if n queries have been made till now, then it will take n square time, because searching in a query is of the order of word length. And we will search for a word of length 1, word of length 2, word of length 3, 4, and so on. So 1 plus 2 plus 3 plus 4 plus all the way up to n, if n queries have been made. So this stream size keeps on growing. We have to keep track of these. We cannot lose these. So it will be O of n square. So you see that query is very costly here. And in fact, query should be fast because this building time can be slightly on higher side since this is one time operation. But query is being done again and again. So it's not an efficient way to do it like that. That will be n square. So one thing you notice is that we are looking for KL and we are currently here. So what if we stored them in reverse order? So instead of CD, F and KL, if we store them as DC, F and LK just in reverse order. Now our job is done because we are currently here. So we will start from this. If L is found or not, L is not there, it's there, but it's not end of the word. So we will move up. We will look for next character in the stream, previous character. This is K. So we see whether K is there or not. K is there and it's end of word. So we return true. Similarly, in this case, let's say we are at negative example and we look for H. H is not there at all. So we will return straight away in O of one time. If it's there, let's say this CD. So D was not there. D is there, but it's not end of the word. So we just take one previous. So is C child of a D or not? So DC is there. So we return true. So worst case will be O of n if it goes all the way up to beginning. And worst case and best case would be O of 1. It may find it here again. And for negative case, let's say the first character itself does not match. There is no child corresponding to H. So it will return here only in O of 1 for this case. But if we implemented this way, then it would have tried to find H, then GH, FGH and so on. And we would have wasted too much time. So I hope this solution is very clear. There is not much here. It's just that based on our requirement, we change the way we store in the try. So we have to match from L, K. So our word is in this order. So this is first character, second. In this way, we will never have to repeat the search for any of the characters. So that's why we are storing in reverse order. So let's write the code for this. It should be easy for you if you are fluent in implementing tries. So you can go through this example. There are a few limitations given here. Word length can be 2000. Each word can be 2000. So number of queries can be at max 40,000. So you see if you don't optimize the query, it's guaranteed to exceed the time limit. So we will need one try class here. So let's implement one try class. And here all the characters are lowercase English letters. So it's just 26. So we can use this one, the simpler version of try, where we are taking array of fixed size. If we had many characters, let's say 128, then probably we would have used the hash map version of try. In this also you can use hash map implementation, although this one is much simpler. End of word is by default false. And we have initialized all the children to null. Next, we need to implement insert. And also we need to implement search. So let's say here, how do we keep track of the stream? So we need This try we will keep to store the words of the dictionary, but we also need to keep track of the streams we have faced so far. So first query is A, so we store A. Next query is AB, so we should store this AB. Then ABC, ABCDE, so we need to keep track of stream. And what should be the effective way of storing it? Since we would search in this way from current to previous, and while searching, either you process the string from last to begin if you are storing in a string, or it's better to store in some data structure where you can push in the beginning also. So if you are using a vector, pushing in the end would be cheaper, but if you push in the beginning, it will take O of n time. It has to shift everything. So we can use a deck here or a list where we can insert in the beginning in constant time. So we will store it in this form. So we store A, then B, then C, D. Since our search will start from current letter followed by previous, then previous, so it's better to append in the beginning. So for that we will use a deck. So that will come here in the stream checker, that will be part of this. So here we will have one try and one deck. Try for storing the words of the dictionary, deck for storing the stream. Let's call it a stream. W in words. So I'm reversing it, but you can handle that here also. So start from s dot length -1 and decrement all the way up to 0. So that's up to you whether you want to insert here or here. But this try is a piece of code which should be independent of the client's concerns. So that's why we will reverse it here. A try class should be the standard try class, and it's up to the client of that code how it uses that try. So that's why we are reversing it here and keeping it the standard try. So reverse and w dot begin from begin till end. So it's reversed now, and then t dot insert w. So I was talking about this. Instead of this, you can write s dot length -1. You pick the character from that index and then move forward. So if t children c minus a, so we have 26 indices corresponding to 26 letters. 0 is for a, so this character minus a. So if it's a, it will be 0. If it's b, it will be 1. If this is null, so there is no branch corresponding to this character, so we are inserting, so we will insert it. So if it's null, then we create it. And once created, move the current try node to that children, and then we will continue until we have inserted all the characters. And finally, for the last character, this will be pointing to the node corresponding to the last character of this string. So for that, end of word is equal to true. So this is a standard try insert implementation. So we have inserted everything, so this part is done. Next is the query. So for query, what we will do, we will stream dot push front, and I have already explained why we are pushing in the front. So there will be slight change in the search for this case. For the try, we are passing a deck instead of a string. And make sure to pass by reference. If we reach a case where there is no branch corresponding to this character that we are searching, then we return false. That means this none of the prefixes of this word is present. Else we continue our search. And if we find end of word beforehand, then we return straight away. Else finally we will return when we found all the characters of the word, but none of them were end of word. So ultimately we will return false. And here we have already added search. So let's see if this works. Search should not return a value. Okay, so I have made this void, it should be bool. This matches here, this matches. So it matches with the answer. So let's go ahead and submit. And the solution is accepted. So we are right here around 73%. It has long test cases and you can see it takes a few hundred milliseconds. Now let's do this in Java and Python. So if you have understood the concept and you are very comfortable with implementing the try, then it should be very easy for you. So the main thing is done in try itself. Here we are not doing anything in the stream checker class. So constructor part is done. So this looks to be done. Now we will implement the stream checker. So we have initialized the two data structures, and next, or we can keep it outside also. So here we had reversed it and then inserted. So let's reverse it. W rev and this part is done. Finally, the query part, and it was also very simple. We have to append in the beginning of this stream. So stream dot add first and letter. And this again matches, so let's submit. And the solution is accepted. So here also it's good, it's 80.5, but Java solution take much less time. Now finally we will do it in Python 3. Here we cannot do character arithmetic directly, so we fetch the ASCII value of C and A and then subtract one from the other. And finally, let's implement the query. And the answer matches, so let's submit. And the solution is accepted.